I recall that we were looking at the case of one dimensional motion in a nonlinear oscillator situation where the Hamiltonian, the function of q and p, was something of the form p squared over 2 plus q to the 2r over 2r, where r is a positive integer, and the case r equal to 1 corresponded to the simple harmonic oscillator. We had computed what the action was for motion in this potential, and we discovered that the action, which was an integral over p dq for bounded motion, oscillatory motion in this potential, was proportional to a certain power of the energy of the oscillator itself, which is e to the power r plus 1 over 2r. This is the result we obtained. Of course, if you translate this back to action angle variables the way we had defined it earlier, this implies that k, the Hamiltonian, as a function of the action is proportional to the action to the power 2r over r plus 1, which immediately implies that the frequency omega of motion, which is defined as delta k over delta I, is proportional to I to the power r minus 1 over r plus 1. If you therefore define a degree of nonlinearity alpha, say, and that is defined as delta log I over delta log omega, then this is equal to r minus 1 over r plus 1, and notice that r equal to 1, which is the simple harmonic oscillator, alpha is 0, no nonlinearity, and as r becomes larger and larger, the nonlinearity tends, as r tends to infinity, to the value unity. So it is a very useful indicator of the degree of nonlinearity, if you like, of an oscillator of this kind. Not a universal measure of any by any means, not a universal measure or anything like that, but a very useful one in many contexts. Okay. We also saw that the semi-classical quantization of this system is immediate. It follows at once, because if you recall, in semi-classical quantum mechanics, semi-classical quantization corresponds to writing I, which is integral p dq, equal to n times Planck's constant, where this is an integer. And if you take that along with this, this at once implies that n is proportional to the energy level E sub n to the power r plus 1 by 2r, or En is proportional to n to the power 2r over r plus 1. So it tells you something about the level spacing for quantized motion in this potential. Is it the other way about? Pardon? Ah, yes, of course, this is log omega over log I, and that is this degree of nonlinearity. Okay. The way the frequency changes as a function of the action. Thank you. So semi-classically we find that the energy level, the nth energy level, is dependent on the quantum number n in this one dimensional problem according to this relation here, valid for n much bigger than unity, which is where the semi-classical rule is valid. And again you notice that when r is equal to 1, so here r equal to 1, which is simple harmonic oscillations, we know that En is proportional to n itself. that is a level spacing which is equally spaced energy levels, and this is exactly what the harmonic oscillator does in quantum mechanics. Of course the exact relation for En is n plus half times h cross omega, and the half arises from so called 0 point motion. The ground represents the ground state energy of the oscillator, but we are not going to get into quantum mechanics here, just to point out that this semi-classical argument is immediately leads to this result, that En is proportional to this power of n for this whole family of potentials. Notice also that as r tends to infinity, we end up with En going like n squared, and that is precisely the level spacing for a potential which rises more and more steeply, infinitely steeply, namely a particle in a box. So this is exactly the same as the level spacing for a particle in a box, in a one dimensional box. So that limit too is correctly obtained from this semi-classical formula. One can go further and actually try to find the correction to this n, corrections to other this quantity here, etc., but we are not going to get into that right now. So much for a little digression on semi-classical quantization, which follows from the arguments we have been giving here. Now let us go back a few steps and ask, what is the reason for having integrability in a Hamiltonian system? So we go back to n degrees of freedom, n freedom integrable Hamiltonian, and ask, what is the underlying physical reason for the existence of n constants of the motion f1 through fn in involution with each other?
The
Yes.
concept of freedom in freedom,
Yes.
is it specific to Hamiltonian?
Yes, the way we have talked about it so far is a Hamiltonian system, the phase space variables come in pairs. So we identify n degrees of freedom, n independent degrees of freedom, which means that you must specify n numbers q1 through qn for me to tell me completely the configuration of the system in real space, if you like. And in addition you need n conjugate momenta to complete the description of the system in phase space, in other words to describe the dynamics of the system. So I call number of degrees of freedom the same as the number of generalized coordinates that I have, number of independent degrees of freedom. In the case of more general dynamical systems, first of all the phase space does not have to be even dimensional. This pairwise structure, the Poisson bracket structure, is not necessary at all, and I do not distinguish between different kinds of variables. I just call the whole set dynamical variables 1 to n, or as many as there are.
For example, in
Yeah.
statistical mechanics,
Yes.
relating to gases,
Yes,
ideal gases, we talk
Yes.
about ideal degrees of freedom.
absolutely.
But it's chaotic motion, as you said earlier. So what
Yes, absolutely. It is the same as the degrees of freedom. If I give you, for instance, in statistical mechanics, when you discuss monatomic gases, diatomic gases and so on, for a diatomic gas you ask how many degrees of freedom does a diatomic molecule have?
chaotic motion, right? It's not Hamiltonian, it's some chaotic motion.
Yes,
So,
yes.
so whereas there's no concept of degrees of freedom.
The question is whether in chaotic motion the concept of degrees of freedom appears or not. Of course it does. It has absolutely nothing to do with the kind of motion. Identification of the number of degrees of freedom.
Establish that all sorts of chaotic motion which occurs in gases is Hamiltonian.
Yes, I would believe so. I would believe so, unless there are other reasons to believe that external forces are present, or there is a time dependent perturbation acting on the system or anything like that. But if I give you a collection of molecules and you assume Newtonian mechanics to hold good, and the system is isolated, they act with forces acting upon each other caused by themselves, then I do not see why it is not a Hamiltonian system.
When you're not able to formulate the system itself, how can you generally say that it's Hamiltonian?
Why do you say I can't formulate the system?
You don't know the exact equation governing them, right?
I assume, let us assume, put a model on it, let us assume that Newton's equations are valid, let us assume that there is a certain potential energy between two molecules a certain distance apart. Once I have a model of that kind, I have a Hamiltonian system with a very large number of degrees of freedom, no doubt. The motion is in general chaotic, it is very irregular, it is not integrable. Yes, it is assumed to be Hamiltonian, yes indeed. Of course in real gases you have many other complications. For instance, you might have to bring in quantum mechanics, you might have to solve the entire problem quantum mechanically. That is a separate subject in itself, we are not going to get into that here, but otherwise yes, it is a Hamiltonian system. The kind of motion that a system has, whether it is regular or integrable or ergodic or chaotic, this has nothing to do with the identification of the number of degrees of freedom you have, absolutely nothing to do with it. So let us look at an n freedom Hamiltonian system, for which the Liouville-Arnold criterion tells us that the system is integrable if you have n constants of the motion f1 to fn in involution. And then we saw that a transformation to action angle variables is possible, and once you make this transformation, the Hamiltonian becomes independent of the angle variables, it is a function of the action variables alone, and then you can integrate the entire 2n set of equations that you have, all 2n equations for prescribed initial conditions, at least in principle you can do this. Now you could ask, what is the physical reason why this system is integrable, why these systems are integrable, what is the physical significance of these f1 through fn. Of course the action variables which we talked about, which lead to the natural frequencies of the system, the omega I, are certain combinations of these f's. So in that sense there is already some physical interpretation for these f's, but can we think of this in a slightly more physical fashion, is there something much more immediate, and the answer is yes. The existence of these constants of the motion is related to some hidden symmetry in the problem, a certain dynamical symmetry in the problem. For instance, if I looked at two harmonic oscillators and the spring constants are the same in the two perpendicular directions, then you would immediately tell me that the Hamiltonian is rotationally invariant. You make any rotation in the xy plane and the Hamiltonian does not change at all. So there is a certain symmetry in the problem, and the existence of symmetry is linked to integrability. So whenever a system is integrable, whenever you have these constants of the motion, there exists a certain dynamical symmetry in the problem. Now let us try to understand what this dynamical symmetry is, at least go a little bit into this. It is a vast subject by itself, but let me at least give the rudiments of this subject. Let us go back and ask, what does a canonical transformation actually do to a system? So we start with a system with variables q, p, and you make a canonical transformation to a new set of variables capital Q and p. What does this do? What kind of transformation is it? Or if you like, if these q's and p's are combined into a phase space variable x, a 2n dimensional vector, then these could similarly be combined into a 2n dimensional vector xi. These quantities are functions of these quantities which preserve the Poisson bracket structure. In other words, we know that qi qj is equal to pi pj is equal to 0, and we know that qi pj is equal to delta ij. Now what is meant by a statement like this? What is meant, for example, by this statement here? What I mean by this is, this implies, if I write out this Poisson bracket explicitly, it implies that a summation from k equal to 1 to n over all degrees of freedom, delta qi over delta qk, delta pi pj over delta pk minus delta qi over delta pk, delta pj over delta qk, this quantity is equal to the delta function. That is the definition of the Poisson bracket in the original coordinates, and if the Poisson bracket structure is preserved, it means you have a relation of this kind for every value of I and j. Similarly, we could write these down as well. Now is it possible to use this matrix J which we had introduced and write this in simpler form? Well, yes indeed, because you already know that I can write any Poisson bracket. I could write any Poisson bracket in more compact form if I use the J matrix. What would that be? It would say, take this quantity qi and take its derivatives take the transpose of this, construct it into a row vector, put the j in between, and then the column vector from the derivatives of this, and that would be equal to delta ij. Okay. So can we combine all these three relations into a single relation, and the answer is yes. Not surprisingly, it turns out that all these relations can be combined. Let me do that here. This whole set of relations is equivalent to saying that the Jacobian matrix of the transformation, which let me denote symbolically as delta xi over this delta x. By the way, this stands for the matrix delta qp over delta qp, this matrix transpose j times delta xi over delta x, this quantity is equal to j itself. It is easy to check that all these relations are summarized in the single line by this equation, this matrix equation. It is not very difficult to verify that this is so. I have used this symbolically just to tell us immediately that it is just the Jacobian matrix corresponding to the canonical transformation. Now what does this tell us? This quantity is a 2n by 2n matrix. Its transpose with a j in between times the matrix must be equal to j itself, the same matrix j, and recall that this j was equal to 0, the unit n by n matrix minus that, and 0. It was a 2n by 2n matrix of this kind. What would you call a matrix such that its transpose times the matrix itself is equal to the unit matrix? What do you call a matrix which obeys this condition? Matrix transpose times the matrix, square matrix, equal to I itself. Well, if it is real, then it is an orthogonal matrix. This is the definition of an orthogonal matrix. The inverse of the matrix is equal to its transpose, that is an orthogonal matrix. If the matrix is restricted to real entries, then of course a unitary matrix is an orthogonal matrix because there is nothing to complex conjugate, but in general the matrix could have complex elements. In our cases here all these are real variables, therefore we do not have any complex elements, so a matrix of this kind is an orthogonal matrix. Can you give me an example of a transformation of coordinates, say, which is represented by an orthogonal matrix? Every rotation, absolutely right. Every rotation in physical space is represented by an orthogonal matrix. In 3-dimensional Euclidean space, any 3 by 3 orthogonal matrix of unit determinant represents a physical rotation of the coordinate system. The simplest of these, of course, as you are well aware, is if you took the xy axes and you went off to x prime and y prime at an angle alpha, then this rotation in the xy plane about the origin is represented by a 2 by 2 orthogonal matrix whose structure is what? What is the matrix representing this rotation? Absolutely, it is just cos alpha sin alpha minus sin alpha cos alpha, and so on in 3 dimensions. You can generalize this to higher dimensions. So orthogonal matrices with unit determinant, with determinant plus 1, represent physical rotations. Okay. That matrix there, which represents a canonical transformation in the 2n dimensional phase space, is not orthogonal because there is a j sitting here and a j sitting there, but by now we have got used to this j appearing everywhere in Hamiltonian dynamics. This is pseudo orthogonal in a certain sense. Such a matrix is called a symplectic matrix. Let me write that down. A matrix M transpose J, M equal to J. So this is some where M is a 2n by 2n matrix. is called a symplectic matrix. So what is the lesson we learned from that equation there? Canonical transformations are represented by symplectic matrices. Just as rotations are represented by orthogonal matrices of unit determinant, canonical transformations are represented by symplectic matrices. Therefore, in exactly the same way that the study of orthogonal matrices tells you everything you need to know about rotations, in exactly the same way the study of symplectic matrices tells you everything you need to know about canonical transformations. So this is an algebraic approach to the study of canonical transformations. Now this kind of equation has remarkable properties, as we will see in a second. The first of which is the following: if I took the determinant on both sides, what is the determinant of J? J was defined by that matrix. The determinant of J is +1, we check this out. So determinant J +1, and it turns out from this equation it follows, if I took the determinant of the left hand side, the determinant of a product of matrices is just the product of determinants, and the determinant of M transpose is the same as the determinant of M. So this tells you at once that this implies that determinant M is equal to plus or minus 1, because the square is equal to 1. It turns out that you can show without too much difficulty, although it is a non-trivial exercise, that the determinant of a symplectic matrix is in fact +1. This is why I mentioned earlier that canonical transformations also preserve orientation. They do not just preserve, they preserve a number of things, among other things they preserve orientation, but this is reflected in the fact that the determinant of a symplectic matrix is +1. Just as orthogonal matrices form a group, the product of two orthogonal matrices is also an orthogonal matrix. Every orthogonal matrix has an inverse and they form a group. In exactly the same way, the symplectic matrices of a given order form a group of matrices. This is a subgroup of the set of all 2n by 2n matrices which are non-singular. So let me write that down. The group of all 2n by 2n real matrices. So we are restricting ourselves to matrices which are real, with real entries, 2n by 2n non-singular. What is a non-singular matrix? The determinant is not equal to 0. In other words, there is an inverse for the matrix. So the group of all 2n by 2n non-singular real matrices is denoted by GL, the general linear group of order 2n over the reals. So this stands for the general linear group. Among such matrices, the symplectic matrices form a subgroup of such matrices. In other words, the product of two symplectic matrices is again a symplectic matrix, all 2n by 2n for a given order. Okay. So it is a subgroup of this thing here, and this group is called the symplectic group, and it is denoted by SP 2n, and it is a subgroup of GL 2n. Therefore, for a given dynamical system with a given number of degrees of freedom n, the study of its canonical transformations amounts to the study of the symplectic group of the same order, of order 2n. Now a great deal is known about the properties of such matrices. So a great deal is known about the symplectic group and what it implies and what its generators are and so on and so forth. Therefore we have a fairly good idea of what the symmetry possessed by a system should be, a Hamiltonian system should be. Under a canonical transformation, a Hamiltonian flow goes to a Hamiltonian flow. Measure is preserved. What do you need for a symmetry of the system though? What do I mean by the dynamical symmetry of a system? What would you say is, given a dynamical system, what would you say is a dynamical symmetry of the system? One possibility is to look at its Hamiltonian, if it is a Hamiltonian system, and ask what kind of transformations leaves the Hamiltonian unchanged. That is one possibility. But of course in the case of a Hamiltonian system you need more than that. You actually must make sure that the transformations of coordinates of the variables is also canonical, so that the structure of Hamilton's equations is unchanged. The most general way of defining what the dynamical symmetry group of a dynamical system is to say a set of a transformation which leaves the solutions unchanged. Maybe takes one solution to another and it mixes up different solutions, but the solution space, the set of solutions of the dynamical equations should remain unchanged. That is what I would call a dynamical symmetry of a system. The full set of solutions must remain, of the dynamical equations must remain unchanged. If I accept that, then it is easy to see what I mean by the dynamical symmetry group of a Hamiltonian system, and let us write that down. By this I mean the dynamical symmetry group of a system is a set of transformations of its phase space variables set of transformations that leave the solution space pardon me, that is sorry I did not get the question. What is F? No, not necessarily. Not necessarily, there is nothing to do with the Hamiltonian system. Right now we are talking about a very general statement. I am simply saying when I have a dynamical system described by a set of differential equations and I ask what is meant by a symmetry group of the system, the most obvious statement is that it is a set of change of variables of the system such that the solutions do not get changed, the set of solutions does not get changed. That is what I would mean by dynamical symmetry group. Now let us come to a Hamiltonian system and ask what is the dynamical symmetry group of a Hamiltonian system, what can it possibly be? Well, what do you need for a Hamiltonian system's solutions to remain unchanged? First of all, I certainly need the following. I certainly need the Hamiltonian system, the Hamiltonian flow to go to a Hamiltonian flow. I certainly need that. This is done by the set of canonical transformations, but I need more than that. I would like to leave the solution space unchanged. In other words, the Hamiltonian itself should not change, so that the equations of motion are exactly the same in the new coordinates as they were in the old coordinates, right. So not only do I need the set of canonical transformations, but I need a subset of this group of canonical transformations which leave the Hamiltonian itself unchanged. In other words, I should not change from h to k, h must remain unchanged. That does not always happen with all canonical transformations. Therefore, the dynamical symmetry group of a Hamiltonian system, for a Hamiltonian system, the dynamical symmetry group is the subgroup of canonical transformations that leave H itself unchanged. So that not only do you go from a Hamiltonian flow to a Hamiltonian flow, but moreover it is the same Hamiltonian, and then you are guaranteed that the dynamical equations do not change, and therefore the space of solutions does not change either. In general, therefore, this dynamical symmetry group of a Hamiltonian system is a certain subgroup of SP2nr, whatever be the number of degrees of freedom. That also could be a group. It may not exist, you may not have much symmetry in the problem at all, and that is in fact what happens in general, but then in those cases where the Hamiltonian is integrable, it turns out that you have a dynamical symmetry group, and in fact that group is generated, the infinitesimal generators of these transformations that belong to the dynamical symmetry group are related to the constants of motion F1 through Fn.
That means that
So,
if we can get a transformation which is in the dynamical system group, its inverse should also be there. Like
yes,
generating
yes, of course, yes. In a group every element has an inverse, so this is certainly true. Yeah. Canonical transformations have inverses. That was our first premise, that going from the small q's and p's to the capital Q's and p's was actually invertible. This was our premise, that the canonical transformations we have talked about are global canonical transformations, namely they apply in all of the phase space concerned. Of course you could have a local canonical transformation which is not applicable in all of phase space. We have not looked at that possibility at all here. We are only talking about global canonical transformations, and they are certainly invertible. In fact, since you raise the point, a canonical transformation is a symplectic transformation, so it satisfies this relation here. And of course what does this imply at once? Let us take this m across to the other side by applying the inverse operator. So it immediately says mtj is equal to j m inverse, and let us bring the j to this side by applying the inverse of j, and therefore I get j inverse m transpose j is equal to m inverse, but I know that j inverse is minus j. J inverse is equal to j transpose is equal to minus j. So in fact I know that m inverse is equal to minus j m transpose j for a symplectic matrix, and therefore the inverse exists. No reason why it should not, this determinant we already saw was +1. So these transformations indeed form a group. The point I am making is that the dynamical symmetry group could be much smaller than this group, than the group of canonical transformations, could be much smaller in general, because I also pointed out that in cases where the system is not integrable you do not have any symmetry at all, but when you do have some special symmetry the system could become integrable. This is the idea here. Let me for example go back to the two-dimensional harmonic oscillator and ask what the symmetry group could be. This is not easy to identify, it is not a trivial task to identify the dynamical symmetry group of a system which we know to be integrable. In general one has to do a little bit of work to do this. So let us look at the two-dimensional oscillator, which is h of q1, p1, q2 and p2, and this was p1 squared plus q1 squared over 2 plus p2 squared plus q2 squared over 2. If I took an oscillator which has exactly the same frequency in the 1 and 2 directions. This is the isotropic oscillator here. This Hamiltonian has a great deal of symmetry. The symmetry group, the group of canonical transformations is the symplectic group in 2 degrees of freedom. So this is sp4 over the reals. What is the group of transformations that leaves this Hamiltonian unchanged? What would you say is a group of transformations that leaves this Hamiltonian itself unchanged? Notice that I can just take out the factor half and write this in this fashion. So I should write here 2D isotropic oscillator. Isotropic to mean that it's got exactly the same properties in all directions. As you can see, the potential energy is q1 squared plus q2 squared, which is invariant under rotations in the q1 q2 plane. So it has circular symmetry this kind. What would you say is the symmetry or the group of transformations of these 4 variables, each of which runs from minus infinity to infinity, that leaves H unchanged? We can switch variables, but there is a big huge continuous group of transformations. What would leave this unchanged, this combination unchanged? If I have x squared plus y squared plus z squared in 3 real variables x, y, z, what group of transformations leaves this unchanged? All rotations about the origin leave it unchanged in the 3 dimensions x, y and z. What leaves this unchanged? All rotations in phase space, in this 4-dimensional phase space, all possible rotations about the origin would leave this unchanged. What would that group be? The symmetry group of H itself. What would this group be? It is the group of rotations in 4 dimensions, 4 Euclidean dimensions. What would that group be? It is a group of 4 by 4 matrices, but what sort of matrices would these be? They have to be orthogonal. What should the determinant of the matrix be? +1, so volumes are left unchanged, and that group is a group of orthogonal transformations in 4 variables called O4, but because the determinant is 1, you write an S here to write special or unimodular, determinant +1. On the other hand, this stands for orthogonal. So on the one hand, the group of canonical transformations in 2 degrees of freedom is sp4r, the set of all 4 by 4 matrices with real elements which are symplectic, which satisfy that condition. On the other hand, this particular Hamiltonian is left unchanged by the group of all 4 by 4 matrices with real entries which are orthogonal and which have unit determinant. It is clear that for the dynamical symmetry group of this problem, the set of transformations in phase space that leaves this Hamiltonian unchanged and takes the Hamiltonian flow to a Hamiltonian flow, does not change the Poisson bracket structure, is that set of transformations which belongs to both this group as well as this group. In other words, the intersection of these 2 groups. So all matrices which are both symplectic as well as belong to this SO4, that set of transformations, that special subset of canonical transformations is in fact the symmetry group of this system. So as you can see, it is not easy to identify the symmetry group of a dynamical system, because not only must the transformation be canonical, but it should also preserve the form of the Hamiltonian. In this case, since the Hamiltonian was so simple, I could do this directly without too much trouble. I could just identify it by inspection. This looks like the surface of a sphere in 4 dimensions, and therefore I could immediately write down SO4. Now that group, which is the intersection of these 2 groups, is a different group altogether. It is smaller than either of these groups, and it is the group of, turns out to be the group of all 2 by 2 unitary matrices with determinant +1. So let me not write that down in explicit terms and get into group theory, but let me just write the result down and say the intersection is SU2, which stands for the group of all 2 by 2 unitary matrices with determinant +1. So it is a set of transformations which can be put into one-to-one correspondence with this set of matrices here, and this requires some mathematics to prove, which we will not prove, but I am going to simply assert that this is so. The reason I do so is because I would like to identify the generators of this group and show you what the physical meaning of these generators is. You see, what are the constants of the motion here? First of all, we know it is integrable. We had two constants of the motion which were in involution with each other, and what were those two constants? One of them was F1, which we could take to be just this, the energy of the first oscillator, and F2 was 1/2 q2 squared plus p2 squared. Okay. What else do you think is a constant of the motion here? It is clear the system is integrable. We know that the frequency ratio is unity in this case, the same frequency for both these oscillators. So on the surface of this torus we talked about the last time, when you go around the torus in this way once, you also go around this way once, exactly once. So the motion is periodic, completely periodic, there is just one period, unit frequency. These two are also in involution with each other. Now to describe the trajectory, you need one more constant of the motion, which is an isolating integral, so that the trajectory does not wind itself around on this torus completely, but rather is a discrete curve, is a curve, is an isolated curve for each set of initial conditions. What else do you think is constant in this problem? Let us think a little physically. Q1 let us say is the x axis and Q2 is the y axis, and you have got a problem where you have an isotropic oscillator, the same spring constant in both directions, and the potential is circularly symmetric. If I write this down in plane polar coordinates, this is just 1/2 r squared. So what do you think is constant in such a motion? Well, here is this particle in the Q1 Q2 plane. Well, the actual shape of the trajectory will depend on initial conditions, it will depend on what the phases are, what the initial values of Q1 and Q2 are, that is certainly true. But what do you think is a symmetry? I mean, what else is constant? What sort of force, if the particle is here and is attached by a spring to the center, what kind of force is exerted by the spring? In what direction is this force? It is always radial, therefore this is a central force problem. It is certainly a central force problem. What do you expect is constant in a central force problem? The angular momentum, that is right, there is no torque on this particle. The angular momentum is therefore a constant of the motion, we are guaranteed that. Now what is the angular momentum in this planar problem? You just have two variables, here is x and here is y, and this is p sub x and that is p sub y. What is the angular momentum? Well, if you use this formula r cross p, since you have reduced to a plane, everything is in a plane, this cross product is essentially a single number. So what is r cross p? There is only one component to it, and what is that equal to? Not P1, P2, Q1, Q2. Think in 3 dimensions. If you have r cross p in 3 dimensions, what is the z component of r cross p? What is the third component of the angular momentum, which I will call L? Or since I know that it is the third component, if I am looking at a 3-dimensional problem, let me just call it J3. What is this guy equal to? Yeah, it is equal to Q1 P2 minus let me put a half here for a reason which will become clear in a second. I am guaranteed that this quantity is a constant of the motion. In other words, the Poisson bracket of J3 with H is 0, that is not hard to verify. So indeed this is a constant of the motion. And now it turns out that the following quantities J1, J2 and J3, which we have already written as Q1 P2 minus Q2 P1. J1 is a quarter of Q1 squared plus P1 squared minus Q2 squared minus P2 squared, and this is a half Q1 Q2 plus P1 P2. It turns out that each of these quantities is a constant of the motion. So indeed it turns out that Ji, Jk or Ji with the Hamiltonian is 0, I equal to 1, 2 and 3. So we have other constants of the motion. These two together with this third one, the isolating integral, actually specifies the trajectory completely. The moment you put these three quantities equal to constant, then in this 4-dimensional space you found the trajectory completely, because the intersection, the mutual intersection of surfaces on which this and this are constant specifies a curve, and that is indeed the phase trajectory for any given initial set. Pardon me? J1 is a, yes, I am not saying they are independent, I am going to come to the significance of the J's a little later, but I am saying F1 plus F2 is the Hamiltonian itself, of course. For integrability you just need two constants of the motion which are independent of each other and which are in involution. They are represented for instance by F1 and F2, but I am actually finding a whole lot of other constants of the motion. For describing the motion you actually need three isolating integrals in this problem, and they are represented for example by F1, F2 and F3 and J3. But in addition these combinations are also constants of the motion. Sure, this is just F1 minus F2 apart from some constant factor. This is something else altogether, and this quantity here is the angular momentum about the origin. But now you can't have more than two constants of the motion in involution with each other, that is for sure. So in fact that is the maximum number that could be independent and in involution. You can choose them as you please with various linear combinations. I would like to choose this because this completely separates degree of freedom 1 from 2 altogether. The others mix it up in some fashion or the other. Now the significance of this J1, J2, J3 is that they obey very interesting Poisson bracket relations, and they obey the following relation. Among themselves you have Ji, J is equal to epsilon ijk jk. This is the totally antisymmetric symbol in 3 dimensions. It is equal to +1 if ijk are a natural permutation or an even permutation of 1, 2, 3, -1 if it is an odd permutation, and 0 in all other cases. This is the Levi-Civita symbol in 3 dimensions. So this stands for a set of 3 relations. J1 comma J2 is J3, J2 J3 is J1, and so on in cyclic permutation. What does this remind you of? This is exactly the relations obeyed by angular momentum components. If you write r cross p in 3 dimensions and ask what is the Poisson bracket of Lx with Ly or Ly with Lz or Lz with Lx, you get exactly this set of relations. So in some funny fashion angular momentum algebra in 3 dimensions is related to the dynamical symmetry group of the 2-dimensional isotropic oscillator, and the reason is group theoretical, it is purely algebraic. It turns out that this group is generated by 3 combinations of Q's and P's which are precisely these 3 quantities. They are, if you like, the generators of this group SU2. So you see what is happening is, to summarize things, here is a system which is completely integrable. It has 2 degrees of freedom. So we have 2 constants of the motion in involution with each other which are functionally independent of each other, and those are F1 and F2. Since the motion is periodic rather than quasi periodic, we need a third isolating integral, another algebraic function of the q's and p's, and that is provided by this quantity J3 for instance, which has the significance now of being the angular momentum about the origin. So we have the energy of the first oscillator, the energy of the second oscillator, and then the angular momentum about the origin. In addition, there are these combinations J1 and J2 such that J1, J2 and J3 are all constants of the motion, but they are not in involution with each other, they can't be, there are too many of them. Instead they obey a certain algebra. The Poisson bracket of any two is a linear combination of the same quantities, in this case just the third one with the appropriate sign. That algebra represents something much deeper. This algebra, the existence of this set of relations implies that there is a certain dynamical symmetry group in the problem which happens to be the intersection of the symplectic group SP4R of canonical transformations in this problem with the symmetry group of the Hamiltonian itself, which happens to be SO4, and that group can be put into 1-to-1 correspondence, the set of transformations, with the group of 2x2 unitary matrices, which is this group here, and this group has 3 generators which happen to be the same as that of angular momentum in 3 dimensions, and that is the reason why you have these combinations J1, J2, J3. So as you can see, dynamics and the algebraic structure underlying integrable equations, they are very closely linked with each other, and this 2-dimensional oscillator gives us a simple model in which to understand the origin of these symmetries in this case. Of course if you go to 3 dimensions and write the oscillator down in 3 dimensions, that is a much bigger group, the symmetry group is much bigger, the canonical transformations would be SP6, R, and then you would have to look at the intersection of that or the subgroup of that which also leaves the Hamiltonian unchanged, and that is a much more complicated group. Turns out that happens to be SU3 in that case, and so on. In fact the n-dimensional isotropic oscillator has a symmetry group which is the same as a set of transformations, the set of transformations that is the symmetry group is the same as the group of n by n unitary matrices with determinant +1, a very useful relationship in many applications. But I do not want to get into that right now. I would like to go back and give you another problem which also you are familiar with, where there is an extra symmetry, and we will see where this comes from. Yes, if the generators is 3, it is exactly the angular momentum algebra. This thing here is, no, it will not be. For example, the 3D isotropic oscillator, the dynamical symmetry group is SU3. In fact the general statement is the n-dimensional isotropic oscillator, n-dimensional isotropic oscillator. I should not call it n because this number n has been used for degrees of freedom, but okay, it is the same number actually, n-dimensional is SUN. So, no, it does not obey this algebra, it obeys a more complicated algebra, but the question you could ask is how many of these are there? That is something we can directly answer. How many generators do you think there are in SUN? Well, let us start from we could start from 1 by 1 matrices, and then we could go on to 2 by 2, 3 by 3, etc. The least trivial case is the simplest non-trivial case is SU2. So let us look at that. We want to look at all unitary matrices, 2 by 2 matrices which have unit determinant. I want to look at the set of all these matrices, and I permit complex entries. Okay, we will come back to what a generator is of a group, since I have to tell you how these groups are generated. What I mean by it is, let us come back and tell you what a generator is a little bit. I do not want to have a digression within a digression. So what is the number of parameters that you need to specify a 2 by 2 matrix? Start with a 2 by 2 matrix with possibly complex entries. We count the number of real parameters always, 8 parameters, because if the matrix is A, B, C, D, and A and B are all A, B, C, D are complex numbers, there is a real part and an imaginary part to these. So in general 8 real parameters are needed. And now I start putting conditions on these matrices. What is a unitary matrix? A unitary matrix is one where U dagger U is equal to the identity matrix. So this is unitary. The dagger stands for the complex conjugate transpose, the Hermitian conjugate of this matrix. So I take the transpose and then do a complex conjugate of this matrix, and I insist that this be true. So what I am insisting upon is that A, B, C, D multiplied by the complex conjugate transpose. So this becomes C star, B star, A star and D star be equal to 1 0 0 1. I insist upon this. How many parameters are left now? How many conditions does this give me? Gives you 4 conditions. So how many conditions are left? How many parameters are left? 4 parameters are left. I now insist that the determinant of the matrix be equal to +1. That is what makes it S. How many parameters are left? 3, and therefore the number of generators is 3. In other words, any element of this group is found by taking certain special matrices, multiplying them by parameters and exponentiating these matrices, and that gives me a finite element, and that is called a generator of the group. So there are 3 generators, and that is exactly the number we found here, 3 generators. I will illustrate what is meant by generator in a minute, but now what do you think it is for SUN? What do you think it is going to be for n squared? It is n squared minus 1. Therefore in 3 dimensions it is 9 minus 1, which is 8 generators, and therefore there are 8 constants of the motion which obey a certain algebra among themselves, more complicated than this, considerably more complicated than this, but that provides you with a symmetry group. Now let us come to the question of what I mean by a generator, and let us go back and do a little bit of elementary algebra here. So I start with the simplest example of a rotation in 2 dimensions in a plane, and let us write the equations down directly. So I start with the xy plane and I make a rotation about an angle alpha to write new coordinates x prime and y prime, and of course I have x prime y prime is equal to a certain matrix acting on xy. This matrix here depends on the parameter alpha, and it tells me x prime is a certain linear combination of x and y prime is a certain linear combination of x and y, and it is well known of course that we have let us call this matrix which represents rotation by an angle alpha, let us call it R of alpha. Now what are the properties of R of alpha? What does a rotation do? It keeps the origin unchanged, it is linear, it is homogeneous, in other words 0 remains 0, the origin remains unchanged, and distances do not change, nor does this coordinate system become a left handed coordinate system. What is right handed remains right handed. So this means that this matrix R satisfies R transpose R equal to I, it is orthogonal which keeps distances unchanged, and the determinant of R equal to +1. Therefore this R of alpha is an element of a group of matrices which are orthogonal 2 by 2 matrices with real entries in this case and with determinant +1. How many parameters are needed to specify a rotation? 1. So this is a 1 parameter group and there is 1 generator. In 3 dimensions you have 3 Euler angles in general, therefore you have 3 generators for SO3. In n dimensions Euclidean space, how many generators do you need for specifying rotations? yn.
Will be n angles.
There are n axes or n angles, and this is precisely the point where I want to stop and we will take this up. That answer is not right, because that tells you something about the nature of rotations itself. Let me redefine a rotation. A rotation is a linear homogeneous transformation which keeps the origin unchanged, for instance, which is orthogonal, distances are not changed, and the determinant is +1. So a right handed system remains a right handed system. And the reason you say n is because you assume that every rotation is a transformation about some axis, and there are n axes, but this is not true, because if I think of 4 dimensions, then of course I could have a rotation which changes in the xy plane but leaves both the other 2 coordinates unchanged. Or if I look at 2 dimensions, there is no third axis, it is about a point. So an axis need not be identified with a rotation. That is an accident of 3 dimensions. It is an accident of odd dimensionality, we will come to that. So the number of generators is the number of independent orthogonal planes you can find. How many planes can you find in n dimensional space? Orthogonal planes like the x, y, y, z, etc. NC2, which is n times n minus 1 over 2, and that is the number of generators. So I will explain, this is a good example to explain what is meant by generators, so some elementary group theory, and then we will take it from this point. Okay. So let me write that down, SON I will explain what is meant by generator next time using this example. We'll take this.